Hello and welcome to Technically Speaking, where scientists and engineers come together to chat about common interests, share knowledge and satisfy some curiosity. I'm Antonia and I'm joined by Emma and Ellie to talk about antibiotic resistance, what it is and what is being done to address it. So to start off with, I thought it might be a good chance to learn from Emma because I think you've done some research in the area of antibiotic resistance.
I actually have, and I think I only realised when we were planning this episode how much stuff I've actually done of antibiotics. But so my master's was essentially looking for like alternatives to antibiotics. I did a lot of research into how they work and what's wrong with them, and did some like lab testing with antibiotics and computational simulations as well. And now actually my PhD, although it's not on antibiotic alternatives, it's very, very close to that. So I still a lot of the papers I read are still about antibiotic resistance. So maybe I am some form of resident expert at the moment, which is quite interesting.
You've done more research than me, so I'm happy to give you the expert title.
Nice.
Oh yeah, for sure. So Ellie, you're not a expert, as you said, in your words, but you did study zoology at university, and did antibiotic resistance come up there?
I was trying to make any link that I could think of between antibiotic resistance and anything I studied at uni, but I can't really think of anything. The best I could do is zoonotic diseases, but I don't know enough about it to be like, yes, and then they developed I don't know, is the honest answer, but I'm very happy that we have Emma, because she can teach me all. The only thing I really know about antibiotic resistance is like MRSA. That's like the best I can come up with, and even that I don't know that much about. So hopefully we will all learn a lot through the course of this episode.
Yes, but on the topic of MRSA, what is MRSA?
So when I think you might think the same, Eleanor, when I was younger and I heard people talking about MRSA, I thought it was in itself like a disease.
Yes.
But what it actually stands for is the SA is a strain of bacteria, and the R stands for resistant. So it's just resistant strains of bacteria that have been given this kind of umbrella term of MRSA, which I didn't actually know for, honestly, a shocking amount of time for somebody who...
No, today I learned. I just assumed it was like some superbug that people get in hospitals, but I didn't realise that it could be more than one disease, or like different bacteria creating different diseases. I'm already confused. Please lead me the way.
The SA is a type of bacteria. It's the A is aureus, and that's nice to pronounce, but the S is hard to pronounce. But it's a
Fair. We won't make you do the Latin.
No, it's a strain. So it's just like E. coli is a strain of bacteria. This SA is also a strain, but it can develop. It's one of the first strains that started to develop resistance, and why people had to get a little bit worried. And so I think that's why it's become this kind of big term for bacterial resistance and antibiotic resistance.
So if we said someone had MRSA, does that mean they have a disease, or is it just they have some resistant bacteria?
I would say they have some resistant bacteria, but if they also have, if they have that bacteria that's resistant, then that bacteria will have the effect of a disease. Like, it'll be a bacterial infection because the antibiotics won't work. So I guess the whole labeling of disease is it just depends on how you want to call it. But I always think in terms of if you have the bacteria and if it's resistant, I always just think of the bacteria rather than like a disease or an illness or something. But I think that's because I'm used to just doing stuff in the lab rather than actually real people.
I guess the bacteria is making you sick, right? So you have an illness regardless because you feel ropey.
Yeah.
And then what's making you sick is then resistant to the things that you would normally use to cure it.
Yeah, exactly. See, expert already.
It's been a whole 2 minutes. I'm already nailing that.
Yeah.
So how big a problem this is. I think you shared with us an article about the number of deaths that could be attributed to antibiotic resistant diseases or death. Infection, which led to death, or was somehow a death related to an antibiotic resistant disease. No, I've definitely messed that up.
No, it's all the it's all the same. But yeah, no. So I actually found another stat that was that if we continue with what we have currently prescribed right now, like the antibiotics that we have right now, and knowing how quickly bacteria can develop resistance to them, there was a bit of a scary stat that the death toll attributed to antibiotic resistance related deaths is expected to be 10 million annually by 2050.
Oh dear.
Which seems like a very big and scary number, and it definitely is. But also, I think that's what's led to a lot of like new research happening about antibiotic resistance and bacteria in general to try and understand how they work and how we can actually move on and start to look for new things, because it was kind of something that people had all these antibiotics and they worked, so everyone was using them, and so people didn't actually, there was definitely a lull in antibiotic resistance groups where people were like, we have this and it works. And now everyone's like, let's make some new things. So it's a scary stat, but definitely I think people are already kind of working on that now.
Yeah, and this article that you shared first estimates about almost 5 million deaths a year are associated. So that's like double in just 25 years. And obviously in that time, hopefully, our medicine would have improved. But sounds like, we need to invest more in finding alternatives to antibiotics. So what makes antibiotics not work on these MRSAs?
I can definitely answer that one. So one of the main reasons why bacteria can develop resistance to antibiotics is, if it's quite helpful to think about it sometimes in the way that humans evolve. Like the bacteria are just essentially evolving to not be affected by these things that are killing them. But the reason why we see this evolution of bacteria is because they have such a short lifespan. So they can kind of mutate and grow a lot quicker than human cells can. So you can observe, in the space of, a few hours, depending on the bacteria, multiple generations. And so it's essentially Darwinism. So Ellie, you might be a bit more of an expert here.
I heard Darwin
me,
and suddenly my ears perked up.
Yeah. So I will, I guess, paraphrase Darwinism, but the bacteria will just develop a random mutation, and that will, that might make them more resistant to the antibiotic, because antibiotics can work in a few ways, but penicillin, which I would say is probably the most famous antibiotic, works by stopping how the bacteria make their cell walls. So when the bacteria try and divide, they can't actually make a cell wall. So the pressure's all wrong. Water molecules can move in and out when they shouldn't. And so it just kind of can't survive.
It's like a balloon with really bad skin that it just kind of pops all the time.
Exactly. And so you could get a resistant bacteria strain that might have something else on its cell wall that means that penicillin can't target it. And so that's just one aspect of the bacteria that an antibiotic is targeting, but there's obviously lots of different antibiotics that look for different things in bacteria. But you just get this resistance from essentially just evolution.
Yeah, they just mutate so fast that they mutate ways to survive, right? So that's what they're trying to do. So if this is targeting their cell wall, then they mutate something that means it doesn't affect it anymore.
Yeah.
I'm trying to remember, there was this fox study, I think, and they were breeding generations of foxes, and then they eventually exhibited more like domesticated traits in a really short time span. I don't know if you could elaborate, but it kind of reminds me of how short bacteria mutation cycle might be, even faster than that, in like a sort of years like span.
I suppose it's like anything, isn't it? If you think like a human generation takes so long for any changes to come through, but bacteria just don't work like that. And even foxes, like their lifespan is much shorter. They can have multiple litters a year, presumably. So like even those generations, and then they grow up, they're not waiting, I don't know, what, 15 years, 13 years to be able to be sexually mature to then breed. Like that's why it's also staggered in people. But bacteria just can, mutate and grow and breed new generations much, much faster. So I guess this is why this is so common, because it's so rapid, right? Like it takes a long time to develop drugs. Potentially we can't keep up with all the mutations that the bacteria are doing.
Exactly.
And we were talking about cell membranes before we went on this little tangent. And I think you did some research as a biophysicist on cell membranes.
Yes, I did. And I would definitely identify as a biophysicist. Some people call me a chemist, which I don't like. But exactly. So what my project was essentially on is that fundamentally human cells membranes are more or less not charged. Of course, it always gets a little bit more complicated than that, but as like a blanket, human cells not really charged, but bacterial cells are negatively charged. And so the physicist in me, and the group came up with it before I did, but was if you have these kind of positively charged proteins get attracted to the bacterial membranes, and they don't get attracted to the human cells. And the idea was when they bind to the membrane, they can stop it from dividing in the same way that essentially penicillin works, by just stopping a process of the replication from happening. And that's essentially like the main, I think, research focus of bacteria and antibiotics. Is essentially the biggest question to ask is, what is the difference between human cells and bacteria cells? Because we do not want to target our human cells, but we do want to target the bacteria. And so there's, as you can imagine, quite a lot of differences, and that's what a lot of people are focusing their research on, depending on these differences, because that's how you get a really successful antibiotic.
How many differences do you think we're working with? Like on a scale of 10, hundreds, thousands?
Oh, I think, yeah.
I hope lots. I feel like that's better. Like the more differences we can target, surely that's more productive for making new antibiotics.
I think it's like even, I don't know, thousands, hundreds of thousands. I think there's just so many, because
so many possibilities.
Yeah, exactly. And I think like a few of the, like penicillin, I don't think, like people discovered it, but it wasn't like synthesized in the lab. It came from some derivative of a product that was used. I think it could have, I'm not sure at this point, but it could have been used for something else, and then people tried it on kind of a bacterial infection. But that kind of targets one specific thing, and so the bacteria have had time to develop resistance to that, and so people are trying to look a little bit more smartly to think, where else can we look to try and target? And so there's a lot of stuff involving looking at how the DNA replicate as well, which is the part that's semi-related to my PhD. So loads of people are really got their thinking caps on to try and think of the different differences.
Is it likely that some of them will become obsolete? Like penicillin's been around for hundreds of years. Is that going to stop being effective at all in the future? Like, is this why we have to make more? Because eventually it will just be like useless as a drug.
I think if we continued to use it and not have others at the same rate, then that is what we would have. But I think because we are kind of aware of that and we're using other ones, it's a lot more difficult for the bacteria to survive when you prescribe, for example, a hospital won't just prescribe one antibiotic, they'll prescribe a lot because they don't want to have everyone always on the same antibiotic. But I do think it's a good point. I think it would happen if we were only using penicillin for everything, which maybe wouldn't even work anyway. But yeah, so it's the reducing using it, and it will still be effective, because I think there's some antibiotics which are really, really, really effective, but very, very risky to have them the bacteria become resistant to them because they're so good. So I think like some hospitals only prescribe those in like really dangerous cases. And I think like that's another example of, I think, scientists being a little bit smart, is there's a lot of backups that are still kind of there that people can still use. And so it's not like this huge panic of what are we going to do? It's kind of like, this is just something we need to be actively thinking about for the future. And yeah, it's kind of nice that people are already thinking ahead of the game.
I just saw Ellie's cat go on screen, and it reminded me about flea treatment for my cat. And they said if you are on a plan with a vet, it's better because they will swap out the treatment if they find one is becoming more prevalent and they can target it, rather than you going to the pet store and just buying whatever off the shelf, because you won't know the sort of trend that is happening. So it sounds like that's what the hospitals are doing, is they're kind of going, okay, loads of people are getting prescribed X, so we're going to make sure that infections don't become resistant to X, so we're going to mix it up a bit.
I just always remember being told to finish my course of antibiotics. Like, that was like really drummed into me as a child, that like you couldn't possibly only take 12 out of 14, that you had to take them all, otherwise the antibiotic resistant bacteria would come for me.
Would come for you.
Otherwise, like, it wouldn't be effective or something, or like it would make the doctors sad, and I was a very people-pleasing child and I would not have done that. But is that like relevant? Is that just something that people tell you?
I think it is. I think it comes from, you want all of the bacteria to be gone, because I don't know, in case over the time that you don't take it, they could develop something. I'm not even sure, to be honest. I think it is so that you don't have any like survivors that can, I don't know, take over your body,
in your system.
Yeah. But I think it's also like a lot of the prescriptions is that there's so much science behind when to give prescriptions to people and how often you should take it and different times a day. And it actually, this is maybe a bit of a sidetrack, but it's really interesting reading drug studies where they change the dosage at different times of the day, but the overall daily dosage is the same. It just depends on when you take it. It has a massive effect on how effective it is.
Wow.
Why? A huge significant difference. I don't know if it's if you take it after you eat, it kind of can be absorbed better or something. That's just a guess, but it's really crazy. So a lot of like drug development studies is with like clinical trials with people, where the people just have different dosages and over different times.
That's wild. Maybe it's all in the timing. I never considered that. Maybe the bacteria go to sleep at like 3 o'clock in the afternoon, so guys when they least expect it.
Or maybe when your own immune system is the strongest at a certain time, or it's woken up.
That's true. Maybe, because it takes me a while to get going in the morning. So I feel like, you've got to hit it while... We said this before about the athletes, right? About the ideal time to compete. With the Olympic one. So maybe it's like similar, that there's like a peak time of day where you're at your optimum, and then maybe if you're unwell you should take it then to like give it the best chance of working. But it equally could just be like it gets absorbed better if you've just eaten lunch.
Yeah, I think
there needs to be further study on that.
yeah.
Tell you what, Emma, this is your next PhD.
Yeah, no, I'll work on it. But it is really, because I always love to find out like what because I think when I've been on some antibiotics, it's actually just been like once a day, and I haven't even thought to take it at the same time. But some people get told to have it after every meal, and so now I'm asking my friends on antibiotic when they're like, "Oh, I'm on antibiotics." I'm like, first of all, when you're taking it, which antibiotics? Because I might have used them in the lab. They might be in my freezer, and I'm just curious to know which ones people are on now that I have a few names.
Are you keeping a log, and you're going to have some kind of meta study to come out?
Things are a lot. I think a few times it's happened since I've started my PhD, and there's only been one that I actually have used before. So I'm still waiting.
And you're not prescribing it straight out of the lab?
That sounds like Emma's offering them willy-nilly to all of our friends. That sounds like how we get antibiotic resistance. Emma is the source after all this time.
Yeah, it's been me. My whole it's like it started in 2022 when I did my masters.
It's not that much of a recent problem, is it? Antibiotic resistance, though.
No, I think it has been around for a while, because I think it comes from the fact that people didn't envision them not really going wrong. So when people started to see this, then they were like, "Oh, we should do something about it." Which I like totally agree with. I feel like if I'm like a doctor and something's always worked, I wouldn't plan for the future and be like, maybe we should think of something right now that also works, because the whole drug development industry can take like 15 years or even longer than that. And like I think it's like 2 billion in the US to go from initial idea to approved and like produced drug. So it's a huge industry. And so I imagine it's a bit of a while ago it was definitely, if it ain't broke, don't fix it.
But also, it is a different job, really, drug development, versus being a doctor or a pharmacist who is prescribing the medicine. Like, you'd have to take time out to figure out that kind of stuff.
No, exactly. There's a whole there's a huge pipeline and loads of different stages of that pipeline. So if I'm working in drug discovery now, I'm kind of just looking at the start of it, which is where you just test loads of different things, see what works, try and understand why, and then from that work to how can we make this better. But then all of the like clinical trials and human trials is stuff that I don't do in my PhD. I mean, I guess it's just like 3 or 4 years, so I wouldn't even be able to, throughout my whole time, if I worked on it completely, get from start to finish, which is, yeah, interesting.
That's so interesting. So should we be worried then? Because they're clearly mutating very rapidly. And as you've just said, the drug, pipeline takes a long time. So, like, is this going to take over? Are they going to, outpace medicine, what medicine can do in the time limit, and PhDs and researchers and everything? Or am I just paranoid?
I think it's a valid concern, because but I also think whenever I read stuff about healthcare, it always is written in a way that is a little bit scary. But especially what I think is really important recently, and it relates a bit to some of the work that I've done, is a lot of people now are using computations and simulations, and especially AI, to kind of shorten that first stage of the drug development process. So it's not like as simple as ChatGPT, can you make me an antibiotic that isn't going to be
that would be so handy,
going to be resistant. But to use tools like that to really, like, where you just have to test loads of different things, instead of synthesizing those individually, which could be like 2,000 to 5,000 molecules, and even then that's quite small already. Sometimes you have like 2 million possible compounds you could do, which is impossible to synthesize those and test those in the lab. Like, that would just take ages. And that's what people kind of used to do, was test all these compounds. But if you use different kind of computational simulations to make the compound, is just kind of a few clicks of a button, and then to test it depends on what you're doing, but you can test thousands in a day, and that will give you this kind of ranking that maybe isn't perfect, but is something to start off with. And then you take those top compounds and you can invest your efforts into testing those better. So I think with the kind of new, and it is very relatively new, I think molecular dynamics computational simulations started in around 2010s, 2015. That is massively changing the drug discovery industry, and I think it's actually really exciting to see where that's going. And I think it's definitely I wouldn't be worried about it, because the computational people are on it, and also the lab people as well.
That's reassuring. I'm glad that you're in the know. You've got a system. I don't know anything about computational simulations or AI, but I feel glad that you do, and that you're using it for good, a force of good in the world against antibiotic resistance.
So with the simulations, is it that you would narrow down things and then someone would actually I can't speak today. So with the computational simulations, would you look at everything and then narrow down some for someone to then actually synthesize in a lab and then move on to the next development process? So it's like adding an additional step at the front.
Yeah, I mean, that's exactly the stuff that I'm looking at. I mean, I do both experiments and simulations. So the idea is that I will then test them myself. But a lot of people are working on, can we narrow it down to, very, very few molecules? And then we do the lab work. And then it's kind of saves everyone time. And what a really important thing about the simulations as well is it's not just that it makes it quicker, but also you can actually see the different atoms interacting, and they're really accurate. They're based on they're trained on experimental studies. So you can actually see where the antibiotic is interacting with on the bacteria. And then you can even mutate the bacteria yourself in a simulation and see, will it survive this mutation? Genuinely.
That's so cool.
And then you can to see how kind of robust your antibiotic is going to be by running these simulations. Because in the lab, you don't get information such as, where exactly does it interact with the bacteria? But in the simulations, you can physically see it kind of moving in and sticking to the area that you want it to. And so it's really cool and really helps people understand actually what's happening with these drugs.
That's so clever. I don't know anything about computer simulations, but I'm imagining manipulating all the tiny parts of it to see what happens if you increase this bit or decrease this bit or make it positively charged or anything like that. And then, I can see how then you could future-proof it as well, in theory. I mean, obviously it takes maybe slightly more time to go from that simulation to what it would be like in practice. Maybe there's probably some disconnect there, but still, it's shaving off hours and hours of work.
And it also... Sorry.
Exactly. I know, I was just going to say exactly.
And it sounds like you might learn something that you didn't know about how bacteria behave, because you've kind of got the rules of physics and biology that you understand, and then apply it to hopefully get the same result in real life, and learn what actually was beneficial about using that particular molecule against that particular bacteria.
Exactly. It really, and I think some people could think that you're not doing experiments if you're doing simulations, but it's just it really kind of hurries along the step and helps you understand even more. There's never a drug that would kind of go out that has not been tested in the lab extensively, but I think it's really interesting to allow people to, even a lot of medicinal chemists you show them a simulation and they can incredibly smart. I can just see the molecule and be like, I know it's going to interact into this area. But it really helps with things like that as well. And it's quite a nice bridging the gap between a lot of different fields. And so I think that I think it's really, really interesting to see how it all kind of comes together. And especially now people are doing so much cool stuff with these computational simulations and comparing exactly with experiments and finding that it just gives, like, when you test it against the same thing, like the same results. So it's a really kind of robust method that I think is only going to get better when, especially like there's better computational power, people can run things from longer and have better kind of do more repeats and do some more stats on it. And it kind of is all fitting together really nicely in this huge information age.
Yeah, it's fun what you say about like different disciplines coming together, because I thought that you were a physicist. And now you're on about testing things in the lab, and I'm like, she's come to biology. She's come to my side. I've won her around.
I think it is funny when my family ask me, they're like, what was your PhD on? And I'm kind of like, DNA. And they're like, what are you doing? It is very multidisciplinary, and I'm learning a lot about chemistry, which has been quite difficult for me because, as you say, I definitely, my master's and my degree was in physics, and so to learn, I don't know, even how to draw a molecule I was like, this is insane to me. But it's helping me. I think it's really interesting, and so it's nice to try and have some physics skills that are coming in a little bit useful.
Absolutely. I do think it's all, like, we've split it purely for our own enjoyment, really, and very much everything is interlinked, so it's good to have a multidisciplinary approach.
Yeah, definitely, because, you know, I guess people have their perspective as well, so you might have seen it from one perspective, and learning a bit of chemistry would help you in your, I mean, back in the day, everyone was a polymath. You know, they just studied everything. And then I think, like, there was a physicist who also got a chemistry Nobel Prize because the two are so linked. You know, in the what I call the Renaissance of the 1900s, where everyone was learning about atoms and that.
There you are, Emma.
Wow, to think how far we've come.
Prize in your future. We can't wait.
I'm hoping I'll keep on working on these antibiotics.
Yeah, if not, we at least got some new drugs.
Yeah, exactly.
We win all round.
Yeah.
On that note, I think that's a good place to leave it, on a nice positive note. Emma's going to be a future Nobel Prize winner. But before that, she's helped us understand a bit more about antibiotic resistance, how we kind of ended up with that, but also how we might overcome that issue with clever planning, about discovering alternatives, about how we use antibiotics today, and then finally the future of computational simulations and how they will all help towards shortening that drug development timeline. So thank you for listening, and hopefully we'll have you with us on another episode.
Bye.
The views expressed in this podcast belong entirely to the person that said them. They do not represent any industry or organisation. If you enjoyed listening to these views, it would really help us out if you could rate us, leave a review and tell a friend. This podcast was sponsored by no one, but if you're interested in funding us to continue to have frank discussions about science and engineering, please get in touch.